Today, as Susan said, I'm going to talk about the generalized SQG equations, and in particular, a very basic problem of just existence, uniqueness, and instantaneous smoothing property of solutions to this equation in the scaling critical sublove spaces. This is a sort of by now classical topic in theory of hydrodynamic equations. But I want to discuss a particular range of the generalized SQG equations that have been conspicuously left open. This is joint work with Mike Jolly and his PhD student, Anuj Kumar. Okay, everybody knows what the SQG equation is, or for the most part, I assume, but I'll be talking about the generalized SQG equation, which contains the SQG equation as one of the points in the family. So this is a family of equations parameterized by what I'm going to view as two parameters: kappa, denoting the power of the dissipation, and beta, which denotes the singularity in the degree of the singularity, essentially, in the constitutive law. So this is an active scalar equation. It's given by, so theta is the scalar that's being advected by the velocity u, and the u depends on theta through this relation. So psi is the two-dimensional stream function. Gradient perpendicular is the perpendicular of the gradient, and this is the Poisson equation satisfied by the stream function. This lambda is the square root of the minus Laplace. So formally, psi is lambda beta minus 2 of theta. And then if we plug this into u, we see that u is minus gradient perpendicular lambda beta minus 2 theta. And so u is essentially lambda beta minus 1 of theta. So let me write that down. So u is like lambda to the beta minus 1 of theta. Okay. The symbol of u is given by, it could also be written as Rees perp. So that's why I just put a squiggle here. So that, of course, that's bounded in all LP. So essentially u is at the same regularity level as lambda beta minus 1 of theta. And I want to make a common distinction, sort of distinction between the various cases that was made as far back as for the dissipative SQG equations. And so the three cases I want to distinguish between are the subcritical case, critical case, and the supercritical case. The subcritical case will correspond to the regime where the dissipation exceeds that of beta. The supercritical one will denote when kappa is less than beta, and when they're equal, we'll refer to that as the critical case. So I'm going to make this distinction later, but this form of criticality, I'm going to abuse that word a little bit during this talk, refers to what I'll call structural criticality. Okay, and the reason why it's called the generalized SQG equation is because at the endpoint beta equals 0, it reduces to the dissipative Euler equation, or sometimes referred to the strongly damped Euler equation. Of course, when gamma is identically 0, and this term is in here, then of course it's just the equation becomes inviscid, and you have the Euler equation. When beta is equal to 1, this is the case of the surface quasi-geostrophic equation. And we see here that u is just the Rees perpendicular of theta. And so u and theta are essentially the same regularity level. And in that case, we have a quasi-linear equation. And then there's an endpoint beta equals 2, which is essentially degenerate because psi is essentially the stream function is essentially theta, and then the advective term vanishes identically. So to make sense of that endpoint, what Che, Constantine, Cordoba, Gancedo, and Wu did was they made the constitutive law more singular by a log. So this is a positive power of the log. So we'll also address some results in that case as well. Okay. So that equation, if we sort of remove or sterilize the equation, if you will, then we see that it essentially has this structure. So we have a linear parabolic evolution on the left-hand side, and then the right-hand side is given by a polynomial in the first derivative of v and alpha derivatives of v. A is just going to denote the negative Laplacian. And so in this more general way of looking at it, structural criticality, I'm just going to refer to as when the dissipation exceeds both of these derivatives. Well, when that'll be the subcritical case. The critical case will be when they're equal, and the supercritical case will be when the power on the dissipation is less than the derivatives appearing in the nonlinearity. Okay, so from this point of view, the Navier-Stokes is structurally subcritical. What I'll call the modified SQG equations when kappa is equal to beta and beta is greater than or equal to 1 is critical. So that's indeed the generalization of the critically dissipative SQG equation. And then what I'll refer to as the supercritical GSQG equation is when kappa is less than beta. All right, when beta is greater than or equal to 1. Okay. So in general, of course, the basic questions are just what is this system well posed? In which regularity classes is it well posed? And what assumptions would you make on F? And the expectations here would be that if F is, for example, real analytic in its arguments, then you should be able to propagate the regularity from the linear evolution. So for instance, when F is real analytic and kappa is greater than or equal to 1, you should expect to propagate analytic regularity. Okay, and so these basic questions were studied in the case of the Navier-Stokes equations as far back as Foyash and Tamam. There were others preceding Foyash and Tamam, but I want to bring up this particular result because I'm going to be talking about Javert regularity. So here are the Navier-Stokes equations, and I'm sorry, I don't think I mentioned this earlier, but I'll be working in the domain I'll be working in will be R2 for the entire talk when it refers to the GSQG equations. So excuse me, in this case, if you consider just the periodic box briefly, then what Foyash and Tamam showed is that if you have a divergence-free vector field, that's a velocity field, which is in H1, and the dot there is to denote that it has zero mean, so the zero frequency is zero. And the, oh, I'm sorry, this capital F should be a forcing term, which is missing, but okay. So if that forcing term is real analytic in space with analyticity radius lambda, then there exists a time depending on the norm of the initial data and the norm of the forcing. This is the Javert norm of the force, so it's this is to be interpreted as e to the k. That's the multiplier associated with this operator. Then you have a unique solution that belongs to that class for all t positive. So you instantaneously enter the Javert class. So I know these results are classical, but I just want to develop some background. So I hope you don't mind. And the key idea here was to develop bilinear estimates in Javert classes. Okay, So essentially continuity type bounds on the nonlinear term. Yeah. So this being the nonlinear term. And since it was introduced to the fluids community, it's since become a classical way of showing that the solution is analytic or is smooth. And so there are many works here: Doring, TT, Gruch, Kukovica, Ferrari, TT, etc. Okay. One can prove results of this kind in a great generality essentially in the generality of the sterilized system that I showed earlier. So if one considers an equation of this form, and f of v, notice now it doesn't depend on the derivatives of v, but you assume that it's real analytic in each of its arguments. For instance, it's a polynomial in v and its components. Then provided that your initial data is in HS, where S is greater than the dimension divided by 2, then you have a unique solution that depends on the size, that depends only on the size of the initial data, and whatever features may go into the right-hand, may go into the nonlinear term here, and you enter a Javert class instantaneously once again. And here the key thing is to develop product estimates. So again, these now this might not be a bilinear term, but you'd like to develop product estimates in a Banach algebra. And of course, this is certainly the case here when S is greater than D over 2. Okay. When F now is allowed to depend on derivatives, so in particular one derivative of V, then you can say more. In general, if you knew that if you work in the space HS where S is greater than D over 2 plus 1, then your solution, you have a local solution that instantaneously enters a Javert class. And of course, the plus 1 is coming from the derivative you lose from the nonlinear term. On the other hand, if you assume that F has, if you assume some additional structure on the function F, so if for instance F is this affine function, then you can lower the regularity class that you work in. So here you work in S greater than between D over 2 and D over 2 plus 1, but of course still a Banach algebra in this case. And these coefficients are analytic, then you can deduce the same result. And so basically the point is, if the more you know about the function F, then the weaker result you can prove, or weaker regularity setting you can work in, and therefore stronger result. So this was general. So this is all in HS, and this was extended to the LP setting by Hantak Bai and Animik Biswas later on, where they show a similar type of result. And now they allow the nonlinearity on the right-hand side to depend on many derivatives of V. Okay, so there are gamma 1, gamma n, and then there's gamma 0 derivatives on the outside. Okay, but the key thing I want to point out is that the assumption in this theorem is that the sum of these derivatives is less than gamma, which is here the power on the dissipation. And so what I want to point out is that this is still strictly a structurally subcritical result, but nevertheless very general. So in this setting, this LP setting, so if you assume that S derivatives belong to LP and S is greater than D over P, then you obtain, they obtain a analogous result to the Ferrari and TT result, where in this generality, as long as S is larger than dimension divided by P plus gamma bar being the maximum of all the derivatives appearing in G, then you have instantaneous smoothing. And if you assume more about the structure of G, then you can reduce the regularity setting even more. Okay, but all of this is for structurally subcritical systems. And as I mentioned in the beginning of the talk, we'll be working with the supercritical or or structurally supercritical generalized SQG. And so it doesn't fit in either of these general theorems. Okay, so I want to talk now about the setting in which we'll work in. So in the setting of those previous general theorems, one was essentially always working in a Banach algebra. Okay, that's not necessarily the case in the setting that we'll be working in. So where we will be working is the so-called scaling critical Sobolev spaces. So the GSQG equations, as you know, or as you may know, has this following scaling symmetry in the sense that if you know theta is a solution to the GSQG equations, and then you rescale theta in this way, then this function will also be a solution of the GSQG equation with the initial data also rescaled appropriately. Under this transformation, one sees that the norm h beta plus 1 minus kappa is preserved under it. And so this is the sense in which I mean that this space, this Sobolev space, is a scaling critical space for the equations. Okay, so in some sense, this is the lowest regularity setting in which you'd expect to have a well-posedness result, because this is where because if you're working in regularity just above beta plus 1 minus kappa, then the scaling will help you. For instance, you can rescale your data to enter. If you rescale into and you zoom into smaller scales, you can enter a small data regime, for instance. But but when you work in regularity settings less than this, then what was giving you small data before now is now inflating your data. Okay, and making it large. The regularity where this where the norm doesn't see this the effect of the scaling is critical for that type of strategy, in that it doesn't seem to help. So this is the lowest setting in which you'd expect well-posedness to hold. Okay. Some history into these considerations, in particular for the Navier-Stokes equations. So the study of the well-posedness of the Navier-Stokes in the scaling critical setting goes back to Fujita and Kato in the 60s, where they established existence and uniqueness of solutions in the scaling critical space LD. So that's the LP space where P is equal to the dimension of the domain, and then also the Sobolev space D over 2 minus 1. So after that work, it actually wasn't picked up for a while, it seems, until Marco Cannone in the 90s and Planchon, where they extended these results to the scaling critical Besov spaces. Since then, the regularity has been brought down to BO1 minus 1 by Koch and Tataru. So this is the largest space for which small data global solutions are known. And then it was shown later by Germain, Pavlovich, and Stafilani that in fact the solutions in BMO-1 are analytic. When one goes to the largest scaling critical space, however, this B-1 infinity, then it was shown by Germain and Bourgain and Pavlovich that one actually has ill-posedness of the equations, of the Navier-Stokes equations, but it's ill-posed in the sense that you lose continuity with respect to initial data. So, so it's known that in the largest critical space you have ill-posedness, And then there's work by Susan and Walter Rusin as well, where they study this phenomenon for active scalars. As I mentioned before, though, especially particularly in the case of BMO-1, it was shown that the solutions of Navier-Stokes all instantaneously enter a Gevrey class. In particular, they're real analytic in space. And so the smoothing result, the global small solutions of Fujita and Kato, those would be analytic by a work of Zoran and Igor. And as I said before, Janan, Pavlovich, and Stefanani showed that the solutions, the Koch and Tataru solutions, are also real analytic. And then Hantak Bai, Annemiek, and Eitan Tadmore showed in 2012 that you also have smoothing for these intermediate non-endpoint critical spaces. Okay, so it's a general phenomenon for the Navier-Stokes equations, but as I said before, the Navier-Stokes equations, at least from the point of view of the structure of it, is a subcritical case. Okay, but nevertheless, one has in the scaling critical spaces this existence of large data, local existence of large data solutions, global existence of small data, global existence of solutions from small data, and subsequently those solutions instantaneously becoming Gevrey, or in this case, analytic. Okay, so of course, I'm going to talk about the generalized SQG equation. So here's a map of results regarding the well-posedness of the GSQG equations. So I apologize for the numbers. This is directly from our paper, but I'll of course point out the ones that are relevant. So the horizontal axis denotes the dissipative, is the power on the fractional Laplacian. So this is the kappa axis, and the vertical axis is what is the parameter for the constitutive law, and so the case kappa equals 1 and beta equals 1 being the very center of the circle represents the SQG case. Okay, and this endpoint right here, of course, when gamma is equal to 0, that's the damping parameter. That's the damping parameter, or the viscosity, if you will. The Euler endpoint is here. Okay, and so the inviscid case is all along this line. And of course, when beta is equal to 2, if one modifies the constitutive law so that it's not degenerate, then one also has results here. So let me point out what some of the known results are. So of course, along the critical line, in particular, this very center, there was a series of seminal works by Caffarelli, Vasseur, Kislev, Nazarov, Wilberg, Constantine, and Vikel, where they gave all different proofs of the global regularity of the critical SQG equations. And in a later work, it was even shown that the critical SQG has finite dimensional dynamics. And this result of global regularity was extended to the remainder of the line by Constantine and others as well. So below this diagonal line, this is the kappa equals beta line, what I was referring to as the critical line. So this is all what I'm referring to as structurally subcritical. And so of course one has global regularity. So in this particular case of the SQG, this is the subcritical SQG now, this particular line. There are results going back to Resnick and Constantine and Wu. And of course, the smoothing has also been done in several works, I believe Dong Li and Hongji Dong. On the other side, the supercritical side, for the supercritically dissipative SQG, one has conditional regularity results, eventual regularity results, but also Javert regularity results in the scaling critical spaces. The results I'd like to talk about today all belong to this northwest corner. So this is the most singular regime of the equations and the least dissipative. And all that seems to be known is that one has eventual regularity results in this box, and also global weak solutions. So this is a work of Omar Lazar and Xu. And the results that we have, that's the main results I'd like to talk about today, are the well-posedness in the scaling critical space, scaling critical Sobolev spaces for this equation. So in particular, small data global existence with smoothing and large data local existence with smoothing. Okay. I want to remark that before this work, there was only one work which treated the well-posedness in this region. And it was a work by Xu and others. And they were able to demonstrate local well-posedness. And so this regime seemed largely untouched. Okay, but so what I'd like to point out, hopefully, is what were the difficulties that went into proving this result and what made it so non-trivial to do. Okay, and one last thing. So there are, of course, two important works I have to mention here. One is the original work of Che, Constantine, Cordoba, Gancedo Wu, and they established local well-posedness, but in a subcritical, scaling subcritical space, in particular H3. So since beta is greater than 1, is between 1 and 2, beta plus 1 is at most 3. And the original paper where this equation was, where the system was introduced, established local well-posedness in H3. This was then reduced by Hu, Kukovitsa, and Zian. So this, I'm talking about, both of these results are in VISID, by the way, where that was then reduced to just off of the scaling critical space. So they were able to establish local well-posedness in H beta plus 1 plus epsilon. Okay. In the in-VISID case, the scaling critical spaces, as we now know, it's expected to be ill-posed at that regularity level. Okay, so this is the best one can expect in the in-VISID case. Okay, so the commutator estimates that were identified in either of those works end up being crucial to use, and we have to use them in in a particular way, so that we can establish the regularity in this scaling critical space for the dissipative counterpart of the equation. Okay, so before I leave the slide, I just want to emphasize our results are in here, and notice that I drew an extra line, beta equals kappa plus 1, because we were able to identify an additional criticality, if you will, being in this particular case where the kappa was equal to beta minus 1. So I'll point out how that arises and what the intuition for that that line is. Okay, so here are the Sobolev and Javert norms that I'm going to be using when I describe the results and talk about the proof. So here is the Littlewood-Paley characterization of the Sobolev norms and the homogeneous Sobolev norms. So of course, these delta JFs are the Littlewood-Paley blocks. They're essentially smooth frequency projections onto annuli, which are centered at frequency 2 to the j. And the Givray norm, so here is what I'll introduce as the Givray operator, will be exponential of lower lambda times upper lambda to the power alpha. And the corresponding Givray norm will simply be the Givray operator applied to the function. From this point of view, this way of defining the Givray norm is very much analogous to the way Bourgain norms are introduced in dispersive equations. So this is somehow capturing the natural regularity of the linear part of the equation. Okay. All right, and so here are some immediate consequences of having a finite Givray norm. So one can immediately show that all higher order derivatives of a function can be bounded if one knows that the Givray norm is bounded. And in particular, the case alpha equals 1 essentially corresponds to the analytic Givray class. Okay, so for instance, if the function is in L2 and this norm is bounded, then f has is real analytic with radius lambda. And this radius lambda, if it depends on a positive power of time, then what you essentially get for free is asymptotic decay of all derivatives, provided that the Givray norm is bounded for all time. Okay, and so this the technique of Givray norms, as I pointed out before, was introduced by Foyash and Taman, and their lambda was essentially lambda equals constant times t. Okay, so it was allowed to grow linearly. And as I said, there's been a host of works using this Givray norm since then, and to many equations, not just the Navier-Stokes or GSQG equations, but many others. Okay. The first such result for the supercritically dissipative SQG equations, so this is in particular the case beta equals 1. So if you remember the graph of kappa and beta, this was this line right here. Okay. So in this case, U is a Riesz transform of theta, and one has the following result from Mura, that you have local existence for large initial data, and in particular, you have some gain in regularity rho. Okay, if your initial data is small enough in this homogeneous norm, then that solution is global. And the big insight in this paper was that the Fujita-Kato approach of essentially a contraction mapping argument, which required one to prove a continuity type bound for the bilinear term in Navier-Stokes, is insufficient for this equation, and it's precisely because of the supercritical dissipation. So kappa being less than 1 in this case, and the approach that was proposed by Mura was then to replace the contraction mapping argument by an iteration scheme that somehow preserves the underlying commutator structure. Okay, so that iteration scheme was simply a linear transport equation where the advecting velocity comes from the previous iteration. Okay, otherwise it's just heat equation with this linear transport. Okay, so that was from Miura, and then the subsequent result for showing that the Miura solutions were analytic, were smooth, in particular belonged to a Givray class, was done by Biswas in 2013. So this essentially amounted to doing a priori estimates on the Miura scheme, approximation scheme, all right, but in a Javret norm. So I just want to point out that for the Navier-Stokes, we were taking alpha equals 1 for the Javret norm, but here we allow alpha to be less than 1 because we don't expect to have regularity beyond what the linear equation would have given you. So these results have Javret regularity, which is sub-analytic in particular, okay? And I haven't specified this lambda t, but t is essentially alpha over kappa, okay? I'll make a remark on that form perhaps later. So the point is that in this work, one just does makes a priori estimates, but in these with respect to the Javret norms. So one would like to extend various product and commutator estimates to Javret norms, and this was successfully done in this paper. All right. So here are so for the supercritically dissipative GSQG equations, there are some problems that arise in contrast to the classical result of Miura. So in particular, the commutator structure is much more nuanced. And in order to prove local well-posedness even in subcritical scaling spaces, one had to use the fact, really use the fact that the multiplier was odd, okay, in the constitutive law. And this allowed one to form many commutators, essentially. Okay, and we'll see that appear here. And I'll point out exactly where the variation in the commutators to the commutator estimates from these two works are needed. So in particular, the scheme that Miura proposed is not good enough because it doesn't allow you to form all the commutators you need. So here's the original one. This doesn't work. And when one is trying to form the commutators that you need for the GSQG equations, you can form some of them with this, but not others. On the other hand, if you switched how you linearize the nonlinear term, then you can form the ones you couldn't form. You could form the commutators you couldn't before, but then you lose the ones that you were able to form with the original scheme. And so, of course, a very naive thing is to simply take a convex combination of them. And it turns out that this doesn't work either. And you're still, even though you're able to form commutators, in fact, you're even able to form double commutators with this scheme, you still, it's still not enough to reallocate the derivatives in a nice way. All right, so here is where the kappa equals beta minus 1 line comes into play. So when kappa is less than or equal to beta minus 1, this is precisely when the coefficient in the nonlinear term, if one is viewing it as a quasi-linear equation, it's when the coefficient is more singular than the dissipation. And so even though you might have supercritical dissipation, you could either have this coefficient in the nonlinear term dominating the dissipation or not. When it dominates the dissipation, this is in some sense a strongly quasi-linear regime. So not only is the dissipation less than the advective derivative, but it's also not stronger than the coefficient of that of the gradient of theta. Okay, and it's in this regime that all of these fail. Okay, so what I want to say, the point I want to make is that the approximation scheme needs to be changed, and it needs to be changed in a non-trivial way. Okay, so we are able to do that, and here are the results. So this is the essentially the extension of both the Miura and the Biswas result. So we establish existence and uniqueness in the scaling critical Sobolev space, 1 plus beta minus kappa. So we have existence and uniqueness, and moreover, we have the smoothing. Okay, and of course, if the data is sufficiently small, just in the homogeneous part of the norm, then the solution is a global one. All right. And we have an analogous result for the endpoint case. The endpoint case is essentially beta equals 2, but then we make it non-degenerate by putting a log here. So this is not an idea of ours. This goes back to Che, Constantine, Cordoba, etc. And we're also able to make sense of we're also able to have an analogous result here. Recall if beta is equal to 2, then this is 3 minus kappa. So we're essentially just working just off of the critical space here. Okay, and so it's not, of course, there is no scaling for this equation. And so we're only able to work just off it, essentially plus epsilon more. Okay. And the highest order term is now given by the velocity rather than the gradient of, this just adds some additional technical complications, but we can deal with them. All right. So let me just sketch the proof. I know I don't have that much time left, but I'll also try not to say too many details, to just give sort of the map. Okay, so this is what usually happens or typically happens in critical spaces. So when one does energy estimates, you know, assuming that you have the proper bounds on the nonlinearity, then one always ends up with estimates of this form. So notice this is, so we're performing this this estimate in the critical, at the critical regularity, and one has a square on the dissipation, right? And so really the only way to deal with this is by borrowing from the heat kernel somehow, okay? And this is something that thing can be done at the level of the dyadic blocks. So what I mean is essentially, if we are just able to remove kappa over 2 derivatives somehow, then we could get, for example, local existence, right? By using Cauchy-Schwarz inequality, for instance. If we were able to remove this kappa over 2 and somehow it exits, it's outside as a constant, okay? When it's outside as a constant, then you would like the heat kernel to kill that derivative, if you will. Okay, and so if you work at the level of the Littlewood-Paley blocks, and these are the types of estimates that you could get. And so here, theta j is just going to be the Littlewood-Paley projection onto the jth frequency. Notice I've divided by theta j, a power of theta j, the critical norm of theta j. So we just have power 1 here. And by Bernstein inequality, you can extract the dissipation as a constant here. And on the right-hand side, you see exactly we were able to take out kappa over 2 derivatives as a constant, okay? And so when there's a slight technicality where there's a bootstrapping that one needs to do, in fact, in order to close the estimates. So one gets estimates in the critical norm, one can then get it at the level of the dissipation, and then one can get it at the level slightly larger than the dissipation in delta. And you actually need estimates on all 3 of these things in order for things to close. All right. Just going to, for example, just looking at this inequality, you can see from Gronwall that the dissipation here is good enough to beat the derivatives that you lose on the right-hand side. So you have a gain of kappa here, but you lose kappa minus delta. And so when you compare the heat kernel to the loss of derivatives, you can transfer that to an integrable power of time. Okay, and so once you're at this point, Hardy-Littlewood-Sobolev gives you time integrability of this norm. And so all we really need in order to make this formal argument work is a suitable approximation scheme that essentially linearizes these bounds, right? And by linearizing, I simply mean that if you had a scheme where you're estimating at the level n+1, then this would be level n, and this would be level n+1. Okay, so here is the scheme. So the first level is just simply the heat equation, fractional heat equation. And then for larger n, for further levels in the approximation, when kappa is above beta -1, so this is what I'll call the weakly quasi-linear regime. So that's when the dissipation beats the coefficient in the nonlinear term. One can simply use Miura's scheme, and everything is okay. But when you're in the strongly quasi-linear regime, it doesn't work. And it turns out that what needs to be added is this term. So notice that this is slightly tricky. So not only did we switch theta n and theta n+1, but we also pulled out only lambda beta -2. Okay. And so from this, and notice that when theta n and theta n+1 are the same, then the divergence of this term is identically 0. And so it vanishes in the limit of the approximation, if of course it converges. So then it then collapses in the limit to the GSQG equations. Okay, so the approximation scheme is essentially this conservation law with a modified flux, and of course with this dissipation. All right, so I'll just now flash some estimates. Of course, if one is now performing the local energy balance to make those formal estimates rigorous. So we work at the Littlewood-Paley level. Notice that I'm just inserting the Javert operator here. And really the only pain that you have in dealing with that comes from the chain rule by differentiating the Javert operator in time. This term can be dealt with if you believe me. And one then has to estimate the nonlinear term. So here are one of the commutators. One of the properties one needs to use is this skew self-adjointness of this operator in order just to get estimates at the level of L2. So that's needed already right off the bat. And one can't form this without this term, okay? Because this would vanish, of course, when this is not there. But in a strongly quasi-linear regime, one can form a commutator from it, and that's what allows one to get estimates in L2. But for the higher Sobolev norms, we localize in frequency, and one essentially can start forming many commutators. All right, so I know I'm running out of time. Let me just say a few words about this. So what one essentially does, so Q is now going to be theta n, all right, and theta will represent theta n+1. And just to make the notation a little more less clear. And we're just looking at the strongly quasi-linear regime. So when one expands the flux that we modified, one has these two terms. This one is the original the original linear transport term of Miura, and here's the new one. And what one does is essentially form commutators by distributing this operator to each factor. Okay, to this, remember, this is u dot gradient u. So we give this to the first factor, give it to the second factor, and then we do something similar with the new term, except notice we're going to do something a little tricky. We're not going to form a full commutator. We're only going to form a partial one. So we're only going to form commutators. We're only going to remove intermediate terms, if you will. So rather than distributing this entire operator into each factor, we're only going to distribute, for example, the Javray part of it, and then half of beta minus 2 and the Javray operator into the second factor. All right. So one then can form many commutators. Here's one, here's one. Then with the other term, here's one, here's one. And then of course, because we had to add new terms, well, the new terms we added are also commutators. And I'll just point out that this original commutator was coming from a paper of Hu, Kukovitz, and Zian. The second commutator that deals with the new term that we modified the flux with required a variation of this where we had to form the intermediate commutators, okay? So this one was just essentially the new ones that were added, new commutators that were formed. And again, here are the other commutators. So in the nonlinear term can be broken up into 5 commutators. And then we have estimates for all of the commutators have this particular form, and we have the estimates we need. And all these parameters here are allow for the flexibility we need so that we can plug in the parameters that we need in order to close the estimates. Okay, so I won't and here's the analogous one for the log case. I made some comments about the proof, but let me not go there. And let me just say that one point I want to make here is that you don't really feel the strongly quasi-linear regime until you try constructing the actual solution. So if one is just doing formal estimates, then one might think that the problem is done and one can stop there. But if one actually tries to construct the solution, then that regime causes one immediately sees that regime causes trouble, the strongly quasi-linear regime. With that being said, there are many things we still want to do, many things to still explore. Let me stop there. Thank you very much.